Do you live in Chile, Argentina, or anywhere along the spine of the Andes? Do you have family in the Maule region, near Linares, near Longavi, or near Colbún? Have you ever looked at a glacier-covered mountain and assumed, because it has always just sat there silently, that it always will? If the answer to any of that is yes, then what just happened beneath a volcano that scientists believed had been completely silent since before the construction of the Egyptian pyramids deserves your full attention. Because that mountain just broke its own multi-thousand-year silence in the most unmistakable way a volcano can communicate with the surface world. It shook. Nevado de Longaví is a 3,242-meter glacier-clad stratovolcano sitting in Chile's Maule region, roughly 53 kilometers from the town of Longaví, 55 kilometers from Linares, and 60 kilometers from Colbún. For its entire recorded history, going back through every written record available to modern volcanology, this mountain has had no known historical eruptions. None. 0 documented events since people began keeping records in this part of Chile. Some assessments place its last significant eruptive activity at more than 6,600 years ago, deep in the Holocene, a span of time so long that the entire arc of human civilization, agriculture, writing, cities, empires, has risen and fallen since this volcano last spoke. And then, in the early hours of May 20th, 2026, at exactly 1:49 in the morning local time, a volcano-tectonic earthquake tore through the rock beneath Nevado de Longaví. Scientists at the Southern Andes Volcanological Observatory, known by its Spanish acronym OVDAS, registered the event immediately. It was a rupture caused by rock fracturing deep inside the volcanic edifice, the exact kind of seismic signature that volcanologists watch for as the earliest warning that a long-dormant system may be waking up. And it did not happen alone. Within the next 3 hours, a swarm of 110 additional earthquakes followed the initial rupture. Not over a week. Not over a month. 110 earthquakes in 3 hours, stacked one after another beneath a mountain that had been geologically silent for millennia. But here's the problem. That was just the opening burst. The activity did not taper off after those first 3 hours, the way a single isolated stress release sometimes does. Over the following 2 days, between May 20th and May 22nd, Chile's National Geology and Mining Service, known as CERNA-GEOMIN, confirmed that more than 400 volcano-tectonic earthquakes had been recorded beneath Nevado de Longaví. 400 earthquakes in roughly 48 hours beneath a volcano with no eruptive activity in the historical record at all. Let that number settle for a second. This is not a volcano that erupts every few years and occasionally has an active week. This is a system that, by every account available to modern science, has not erupted in over 6,000 years, and it just produced more seismic activity in 2 days than monitoring networks had ever recorded from it before. And this next part matters because the earthquakes themselves were not weak background tremors. 4 of those 400-plus events registered a local magnitude greater than 3, 0, which volcanologists classified as moderate to high energy releases for this specific system. The largest of them all, a magnitude 4, 3 event, struck at 12:49 a.m. on May 20th, the very same morning the swarm began. CERNA-GEOMIN's official report stated plainly that this was the highest local magnitude earthquake ever recorded in this volcanic system since instrumental monitoring began. Not just unusual, not just elevated, the single largest seismic event this mountain has produced since scientists started watching it with modern instruments. Most people are missing the deeper significance buried inside the technical details of where these earthquakes were actually happening. The seismic data showed a new source location, approximately 4 to 5 kilometers southwest of the crater itself, at a depth of around 3 kilometers below the surface. A new seismic source, not a repeat of historical background noise from an existing, understood fault structure, but an emerging point of stress and fracturing in a part of the mountain's internal plumbing that had not previously been a focus of activity. When volcanologists see a new source location appear, paired with the system's largest ever recorded earthquake, it tells them something specific. The internal architecture of the volcano, the rock layers, the magma pathways, the structural stress field built up over thousands of years of dormancy, was actively being reshaped in real time. This is where it becomes dangerous to treat this as background noise. In addition to the violent volcano-tectonic earthquakes, the seismic network also picked up something else: 5 long-period earthquakes and 1 sustained tremor event. These are different from the sharp, rock-fracturing volcano-tectonic quakes. Long-period earthquakes and tremor signals are specifically associated with the movement of fluids deep within a volcanic system. Things like magma, hot gas, and pressurized water shifting through cracks and conduits underground. Scientists describe these fluid-related signals as low energy at this stage, with reduced displacement readings of less than 1 centimeter squared. Small, for now. But their mere presence, appearing for the first time alongside the largest earthquake swarm this volcano has ever produced, told scientists that this was not purely a rock-cracking event caused by some unrelated tectonic stress passing through the area. There were early signs that fluid movement, the kind directly tied to magmatic systems, was also occurring beneath the surface. What happened next changed how Chilean authorities were treating the entire situation. At 6:17 p.m. on May 22, 2026, just 2 days after the swarm began, Cernajomen formally raised the volcano's alert level to yellow, the second tier on a 4-color scale that runs from green through yellow, orange, and finally red. Yellow specifically denotes an active volcano showing changes in the behavior of its baseline monitored parameters, exactly what had just been documented. Within the same window, Chile's Regional Disaster Prevention Service, CENIPRED, working in coordination with the Maule Regional Presidential Delegation, declared what officials call a preventive early warning for the communities of Longavi, Linares, and Colbún, the very towns sitting tens of kilometers from the summit. A 3-kilometer restricted access perimeter was established around the crater itself, formalized 1 day later through an official government resolution. And in a detail that underscores just how seriously this event was being treated across an entire international border, the Argentine Mining Geological Survey's own volcanic surveillance observatory, watching the same mountain from across the Andes, independently raised its alert level to yellow as well, just 1 day after the Chilean alert. 2 separate national monitoring agencies in 2 separate countries, reaching the same conclusion within 24 hours of each other based on instrumental data from the same restless mountain. Here is why this is serious in a way that goes beyond the raw earthquake count. Cernajomen's own official assessment described this seismic episode as the most energetic seismic process observed at Nevado de Longaví since the very beginning of its instrumental monitoring. Not a notable bump. The most energetic episode on record, full stop. And officials were explicit in their technical reporting about what that meant for risk, despite there being no record of historical eruptive activity at this volcano. Given the signs of internal instability observed over those critical days in May, they stated it could not be ruled out that sudden, precursor-free, low-magnitude explosions could affect the upper part of the volcanic structure, within roughly a 3-kilometer radius of the summit. Precursor-free? That phrase is doing a lot of work in that sentence, and it deserves to be unpacked carefully because it represents one of the most unsettling realities in all of volcanology. Most explosive activity at active, well-studied volcanoes is preceded by detectable warning signs, rising seismicity, ground deformation, gas emission changes, that give scientists at least some lead time to issue warnings. But at a volcano with no historical eruption record, where the internal plumbing has never been observed actually delivering magma or ash to the surface, scientists cannot rule out that the system could produce a sudden small explosion with essentially no additional warning beyond what has already occurred. The 400-plus earthquake swarm itself may already represent the only warning this mountain is capable of giving before something happens at the summit. Now the focus shifts to what happened after that initial dramatic spike, because the story of Nevado de Longaví did not end with the yellow alert in May. It evolved into something scientists describe with careful, watchful language that itself reveals how seriously they continue to take this situation. In the days immediately following May 22nd, seismicity gradually began to decline. A few isolated seismic events were recorded between May 21st and May 31st, with overall activity drifting back toward levels close to what scientists call the volcano's baseline. By the first week of June, the weekly volcanic activity reports coordinated between Cernajomen, CENIPRED, and Argentina's SEGAMAR confirmed that seismicity had continued to gradually decline following the original swarm. On the surface, that might sound like the danger has passed, but that is not the real story, and Chilean officials have been remarkably direct about why. The alert level has remained at yellow continuously since May 22nd, through the end of May, through the first week of June, through the second week of June, and up through the most recent reporting available. It has not been downgraded back to green. The preventive early warning for Longavi, Linares, and Colbún has remained continuously active the entire time, with officials stating explicitly that it will stay in force until conditions warrant otherwise, language that places no fixed timeline on when this elevated watch might end. And the monitoring data tells you exactly why officials are being this cautious. Official reporting covering the full month of May confirmed that, in total, the volcano registered 486 volcano-tectonic seismic events between May 4th and May 31st, the overwhelming majority of them packed into that explosive 48 to 72-hour window, starting on May 20th. That monthly total also included 14 additional long-period seismic events and one more tremor event tied to fluid dynamics within the system, on top of the original 5 long-period quakes and tremor from the initial swarm. The fluid-related signals did not stop appearing after the initial burst. They kept recurring in smaller numbers, week after week, a persistent low hum beneath the mountain's surface, even as the sharp, rock-fracturing earthquakes tapered off. By early June, Satellite monitoring of sulfur dioxide emissions, one of the most important tools scientists use to detect whether new magma might be approaching the surface, showed only low-level contributions, and officials reported that other measured parameters had not shown significant changes through the first full week of June. That is, in one sense, reassuring data. It suggests that, as of the most recent reports, there is no clear evidence yet of fresh magma pushing toward the surface in large quantities. But here's why this is serious enough that scientists are not closing the book on Nevado de Longaví. Cernajaman's own technical assessment, even as it documented the gradual decline in seismicity, concluded that the May seismic episode represented what they called a transient destabilization of its base state. That is the careful, technical language scientists use when they are not yet willing to say the system has simply returned to normal. It means something inside this volcano's internal stress structure shifted in late May, in a way large enough and energetic enough to register as the most significant seismic event this system has ever produced. And the underlying cause of that shift has not been definitively explained away as something harmless and routine. One more thing you need to know about why a volcano with zero historical eruptions deserves this level of sustained, cross-border, multi-agency monitoring. Dormancy itself is not the same thing as safety, and the deeper scientific community has been making exactly this point with growing urgency in recent months, completely independent of what is happening at Longavi specifically. Researchers studying Volcano in Greece, a system that appeared completely silent and extinct for more than 100,000 years, published findings this year showing that enormous volumes of magma had been steadily, invisibly accumulating deep within its magma chambers the entire time, hidden from any surface indication. Their conclusion, published through an international research collaboration, stated directly that a prolonged period of volcanic silence does not mean a volcano is extinct. Instead, it can signal the slow buildup of a large and potentially more dangerous magma system, precisely because volcanoes that have not erupted for tens of thousands of years are routinely labeled extinct and given minimal monitoring resources, right up until the moment they demonstrate, often abruptly, that the label was wrong. That same research community has documented other similarly dormant systems crossing the same threshold in just the past year. Taftan Volcano in southeastern Iran, silent for an estimated 700,000 years, was found to have physically risen 5 inches over a 10-month period, a slow ground deformation signal coming from gas accumulation above a magma reservoir sitting more than 2 miles beneath the surface, ruled out as being caused by rainfall or nearby earthquakes, meaning the push was coming from internal processes inside the mountain itself. And the most direct, vivid historical comparison of all comes from March 2021, when Fagradalsfjall in Iceland erupted for the first time in roughly 6,000 years, almost the identical span of silence now being cited for Nevado de Longaví, following weeks of an earthquake swarm that, at its peak single-day count, also produced approximately 400 earthquakes in roughly a 7-hour window, a number startlingly close to what Longavi just produced across 48 hours. That Icelandic eruption arrived with bright lava oozing from new fissures in the earth, visible from up to 20 miles away in the dark, marking the first eruption the entire Reykjanes Peninsula had experienced in 781 years. Fagradalsfjall did not produce a violent, explosive, life-threatening eruption. It produced a relatively gentle, effusive lava flow that became something of a global tourist phenomenon, drawing visitors who hiked out to watch glowing lava ooze across the landscape from a safe distance. That is the more reassuring end of the spectrum of what a 6,000-year dormancy break can look like. But it is not the only possible outcome. And this is where the human stakes around Nevado de Longaví come into sharper focus. The communities under the preventive early warning are not abstractions on a map. Longavi, Linares, and Colbún are real towns, home to families, farmers, schoolchildren, and elderly residents who have spent their entire lives under a mountain they were taught was essentially inert, a beautiful glacier-covered backdrop rather than an active hazard. Linares alone serves as a significant regional population center for the Maule region's agricultural economy, an area known for wine production and fruit farming that depends on predictable water flow from the Andes, snowpack, and glaciers, the same glaciers that sit directly on top of Nevado de Longaví's summit. That detail carries its own specific danger that has nothing to do with explosions or ash and everything to do with what happens when heat interacts with ice. The volcano is described by geologists as glacier-clad, meaning its upper slopes carry a permanent ice cap. If volcanic heat, even relatively modest heat from fumarolic gas activity or minor subsurface unrest, begins to interact with that glacial ice in a sustained way, it can trigger lahars, fast-moving slurries of melted ice, volcanic debris, and mud that travel down river valleys at speeds that can outrun a person on foot and destroy everything in their path for tens of kilometers downstream. This is precisely the mechanism that made Colombia's Nevado del Ruiz eruption in 1985, one of the deadliest volcanic disasters of the 20th century, when a relatively modest eruption melted enough summit ice to generate lahars that buried the town of Armero and killed more than 23,000 people, the vast majority of them not from lava or ash, but from mud and meltwater moving down valleys they called home. That historical comparison is precisely why scientists watching Nevado de Longaví are paying such close attention not just to earthquake counts, but to gas emissions, ground deformation, and any sign of thermal anomalies near that glacier-covered summit. As of the most recent reporting in early June, sulfur dioxide emissions remained at low levels and other monitored parameters showed no significant changes. That is the good news, as far as it goes. But the yellow alert and the preventive early warning covering those three communities remain in force precisely because officials know that low-level signals today do not guarantee low-level signals next week, particularly at a system that just demonstrated, through hard instrumental data, that it is capable of producing the most energetic seismic episode in its entire recorded monitoring history, with essentially no historical baseline to compare it against. For the people living in the shadow of Nevado de Longaví right now, the experience of the past month has been one of watching a mountain they never worried about suddenly become the subject of government safety perimeters, by national monitoring coordination, and daily volcanic activity reports referencing their hometowns by name, farmers checking on crops within sight of that glacier-clad summit, families in Linares hearing their community named specifically in official preventive early warning bulletins for the first time in living memory. None of them asked for this. None of them had any reason to expect it. A volcano that had been silent since before recorded history simply decided, sometime in the early hours of May 20th, 2026, to start shaking. And here's the uncomfortable truth that sits underneath everything scientists have published about this event. A 6,000 plus year dormancy period means there is essentially no historical playbook for what comes next. Volcanologists studying systems with frequent eruption histories can compare new unrest to past episodes and offer reasonably confident assessments of likely outcomes. Nevado de Longaví offers no such comparison. Every single data point coming out of this volcano right now, the magnitude 4. 3 earthquake, the new seismic source location, the persistent long period and tremor signals, the gradual but incomplete decline in activity, is being interpreted essentially from first principles, because nothing quite like this has been recorded at this specific mountain since modern instrumentation existed. That is precisely why the yellow alert has not been lifted. That is precisely why 2 separate national governments continue independently tracking the same data. And that is precisely why the preventive early warning for Longaví, Linares, and Colbún remains, as officials themselves have stated, in force until conditions warrant otherwise, with no fixed end date attached. The earthquakes have slowed. The mountain is, for the moment, quieter than it was during those explosive 48 hours in May. But quieter is not the same as resolved, and the scientists who spend their careers studying exactly this kind of long dormant system know better than anyone that the absence of new earthquakes this week does not mean the underlying process that produced 400 of them last month has finished playing out. 6,000 years of silence just ended with the loudest seismic signal this volcano has ever produced. What comes next? Gas emissions that begin climbing, ground deformation that starts accelerating, or simply a slow return to a new and uncertain baseline is still being written in real time, monitored hour by instruments that, until this May, had never once needed to ask the question this seriously. Is this the beginning of something, or merely the mountain clearing its throat after 6 millennia of silence?